Guys, in the last video, we discussed this chlorine molecule. That's kind of the mass spectra that we were looking at before that video stopped. And we said that we had really two choices of compounds here. The question just wanted to know what is the structure, and we're just assuming chemical structure for now because we really haven't talked about anything other than that. But there's going to be a point in time where we are going to have to identify the exact molecule that is showing up on that spectrum. So this is our first kind of step in that direction. So both of these have the same condensed structure, and this is the way that we answered that question and kind of left it hanging. But we said there's actually two choices here that can go on. I could have the chlorine at the end of a straight chain carbon, or I could have the chlorine kind of here in the center, and this makes a different molecule because it's not on the end, it's in the middle, but it has the same number of carbons, same number of hydrogens, same number of chlorines. And we said we have to look at the Frag pattern. The Frag patterns are going to be very important because that will help determine which exactly one of these that I have. So the very first alkyl or the Frag pattern that we're going to talk about are the alkyl halides. So the alkyl halides are basically my bromine and my chlorine. Again, I don't really see fluorine on there as much. It's too reactive and organic. I don't really see iodine on there as much because it's super big and super fat, and the thing is not very stable because of it. It doesn't stay around very long. Iodine is almost like the ugliest one of the bunch. Nobody wants it. So alkyl halides have a tendency to do a trend when they begin to fragment. However, it's not just one thing that they can do. The very first one is going to be pretty easy. In the first option, you would find your halogen and you would cleave it at that spot. And the reason is because we've already talked about the bromine being electronegative. Chlorine is also electronegative. They're all grouped right there near fluorine. And we said they're electron greedy. Because they're electron greedy, they don't mind carrying the negative charge. So the first route of cleavage that can happen with a halogen is at the halogen itself. And if it cleaves at the halogen, we have a special term for this, and we call this heterolytic cleavage. I forgot an A. Cleavage. So we have heterolytic cleavage that begins to happen. All right, so this is going to be option number one. Typically, these chlorines get the negatives, and the other piece that's left behind will get the positives. That's route number one. That's kind of what we would have assumed. That's kind of what we did in our previous video when we didn't even know about heterolytic cleavage. The second option, I'm going to change the color here. Of course, I don't know if that's going to be that dramatic, so let's change it again. The second option is at the alpha carbon. And if it cleaves at the alpha carbon, this is what we would call a homolytic cleavage. All right, well, what's alpha carbon? So here's the halogen, and the carbon that the halogen is attached to is called alpha carbon. So this is the alpha carbon right there. And here's the chlorine, and there's the carbon that chlorine is attached to. So this is called the alpha carbon, and that's what we're referring to in each one of these cases. So when we say that the alpha carbon can cleave, what we're saying is that in option number 2, if we don't cleave it at the halogen bond, we can go to the carbon that the halogen is attached to, and we can maybe cleave it there. So this would be option number 2. Now, here in option number 2, or in structure number 2, we've got a couple of things that could happen, but don't let it fool you. We could actually cleave it here to the left and get one CH3 group to pop off, and we have all of this that's left behind. Or we could kind of cleave it here to the right, but you know what? That still just gives us a CH3 group to pop off and the same stuff that's left behind. So these things are symmetrical. They're not really giving me two different choices there. All right? So because of that, we're just going to erase that option can even exist, because it's going to give me the same products. It doesn't matter. It gives me the same thing. So we're just going to say this is our only kind of viable option for number 2, no matter which side. And it could do it to both. If it's a different product, it could do it to both sides, the left hand and the right hand. But because if I cleave it on the right, I get the same pieces as if I cleave it on the left, we're just going to say that's the only option that we've got to deal with. Well, there's some 2 fragments. Out of the two, option number 1 is going to be better. What we typically see is the halogen will go off on its own and it will leave behind the other pieces. The more stable base peak happens with the heterolytic cleavage every time. Well, maybe not every time, but most of the time we can kind of depend on that. Okay, so let's look at option number 2, because we really didn't assign a positive charge to one of those fragments, did we? The only thing that we did is we said, hey, well, it can cleave here and it can cleave there, and these are our pieces. So I'm going to clear out this screen. I'm just going to kind of do a summary up here at the top. So CH3, CH2, CH2, and Br. Or no, sorry. We had chlorine, not bromine, but it would happen the same way with bromine. Doesn't matter, but let's keep it consistent here. And then CH3, CH, CH3, chlorine. Option number 1 is our hetero. There's my sound effects. It cleaves at the halogen. The halogen is electronegative. It takes with it the negative piece. Then that means that the fragment that's left behind are the positives. So in the heterolytic cleavage, this would be a positive fragment, and this would be a positive fragment. In both cases, remember, these are 2 different structures. That means that the weight of the fragment here would be 12, 12, and 12, 36, 37, 38, 39, 40, 41, 42, and 43. Well, if we do the weight of that fragment, 12, 12, 12, 36, 37, 38, 39, 40, 41, 42, 43. Gives me the same fragment weight. That's not really going to help us to determine it, is it? Remember, these 2 molecules are identical with the same number of carbons, same number of hydrogens, same number of chlorines. The M peaks are going to be the same. If I do a formula weight for each one of those molecules, I get the same number. And now we understand that if we have a heterolytic cleavage and I chop the chlorines off and I leave behind these fragments that get analyzed on the mass spec, both of those fragments are 43. that means it can't use that to do its job either. So we've got to look at the other fragmentation patterns. That's why we have more than one fragment. We've got to analyze all of them. So in the next option, we said that we would have option number 2, Homo. The Homo cleavage. So how does this thing actually work? All right. So let's say that we have CH3, CH2, CH2, and Cl. And I told you that we need to take a look at the alpha carbon, right? So I'm going to go ahead and label the alpha carbon just so that you can get comfortable with that notation or that name. This would be the alpha carbon. I'm using that little sideways fish. That's the symbol for alpha. This is the alpha carbon, meaning that cleavage will happen at the alpha carbon. All right, and I'm going to rewrite the second choice down here at the bottom. CH3, CH, CH3, chlorine, and here is the alpha carbon. All right, I'm just going to circle this so that we can pay attention to that area. That's where homolytic cleavage is going to come from. So homolytic cleavage for these molecules means that I'll look at the alpha carbon, and at the alpha carbon, I'm going to break a bond. Well, this one only has one bond for me to choose from, and that's here. That bond will cleave. The one down here at the bottom, we've talked about this before. The left hand is the same as the right hand. It will both spit off a CH3 in either case. Really doesn't matter. I'm just going to draw one option here, and I'm going to cleave that bond. Now this is where things get a little different. That piece will cleave. However, it's not like what happens up above. This bond is made up of 2 electrons, right? The bond between the CH2 and this CH2, in between those 2 carbons that hold them together, are 2 electrons. When we talk about this bond cleaving, what will happen is that this bond will split and this electron stays with this piece. But we already said chlorine or bromine, if that's the case that I've got, they're electron greedy. They will go out and look and scour for any electron that they can, and they'll pull it in as close as possible. So this electron, when that bond cleaves, that electron actually gets sandwiched in here between the chlorine and that CH2 group. So what happens is that I create a fragment here. One of the fragments, CH3, CH2. The other fragment is this CH2 with a chlorine that was there, but now we have an extra bond in between them. And that extra bond has came from those electrons that it has sandwiched and gathered and pulled in to the picture. All right. With that said, this chlorine now has overextended itself, and this guy becomes positive. And this is the positive fragment that gets seen by the mass spectrometer. Same thing's going to happen down here at the bottom. What can happen is that this bond will cleave, and away goes CH3. What we have left over now is a chlorine with a CH group and a CH3 group. The electrons that were kind of in this bond split, and it forms a double bond between that chlorine and carbon. When that happens, chlorine says, oh no, I messed up. I took in too much. I shouldn't have done it. But now it gets the positive charge. And this is the fragment that gets seen in that scenario. So under the homolytic cleavage, this is a 35. Let me pull up the calculator so you could go with me. That's a 35, a 12 from the carbon, 2 more from the hydrogen. This is a 49. If I do it to the bottom piece, the chlorine is 35, the carbon is a 12, and that one has 1 hydrogen on it. I have another carbon from a 12, and then that carbon has 3 more hydrogens, and that gives me a 63. So these are 2 fragments that would be different in the homolytic cleavage part. So now I need to go back to that mass spectra. So let's pull it up. And here's what led to all of this discussion. Well, it seems to me that if I pull this back up here, 43 and 43 is going to be present in both. No matter what we do, they're going to be present in both, right? And it looks like 43 is the base peak. So that one's not a problem, right? 43 was going to happen in either one of these scenarios. Who cares? We can't use that as a judgment. What we can use, though, is the second way that halogens prefer to cleave, and that's the homo end. And this scenario would give me a peak of 49, and this scenario would give me a peak of 63. If I can find one, that's all that matters. Here's my 63. Look at there. The other option, that was 49. 40, 41, 42, 43, 44, 45, 46, 47, 48, 49. Right here. Look how pitiful. Look how tiny. It's hardly even noticeable on the screen. So that means that if I had to give you a full-blown structure, not just a condensed structure, but a full-blown structure, this would be my choice. And the reason is because this molecule can cleave at the alpha carbon and create a positive fragment on this side that gives us this 63 peak. The other option did not do that. The other option gives us problems instead. All right, folks, so again, my microphone actually crapped out on me. So I don't know how much of that you got and how much you didn't get. So I'm going to do a quick review. So we said we had these 2 choices, right? Option number 1 and option number 2. And it looks like on this mass spectra, we said that the mass spectra, both options would give us a 43. So if I look at the MS, the 43 is going to be present. I mean, it's right here. It is the base peak, and no matter which one that I choose, that's going to give me a 43 without a problem. I've got to look at the other fragmentation patterns in order to make this decision. So we went back to the drawing board, and we looked at the homo cleavage. And we said that the homo cleavage in round 1 gives me a 49, and in round 2 gives me a 63. So if I go back to the spectrum, I actually see a 63. It's right here. And 49 is this tiny little bitty one right there. Again, I can't hardly see it. So that would lead me to believe that this molecule is the actual proper choice when it concerns structure. Yes, this is correct. Maybe it just wants a condensed structure. Just simply how many carbons, hydrogens, and chlorines does it have? And this is where I could stop. But if it says what is the real structure, what is the actual structure for this compound, then the only choice that makes sense here out of the 2 is going to be this one. Because an alpha cleavage will happen, This gives me a positive fragment, and that positive fragment is the 63. Option number 1 does not give me that choice. I cannot get a 63 from that. And this 63 looks pretty high on the MS spectra. All right, so if I had to name this, I wouldn't ask you to do this on a test, but just a quick review of organic if you're in that class. This is a propane group because 3 carbons are the main chain. And we always start that off with the proper ending. Propane. It is an ANE, and the reason is because they're all single bonds all the way down the row. So propus 3, ane are single bonds, and it looks like there's carbon 1 and carbon 2 and carbon 3. It looks like on carbon 2 we have a chlorine group. So we would call that 2-chloropropane, or isopropane if you want to give us a common name instead. Okay, so now you're starting to see the nuts and bolts of interpreting mass spectrum, or spectra, because there'll be more than one that you'll have to do. And all of these pieces go together. There's no easy way to really dissect these. You're just going to have to find your own way that you like to start, and then start breaking it down to figure out what in the crap is going on around you. And you're probably thinking about that right now. So this is just another example. There's plenty of more to come. But in the next one, we'll talk a different fragmentation pattern. Alkyl halides are not the only ones that we'll see. We can also look at other common fragmentation patterns with various functional groups. And we'll talk about the next one in the other upcoming video.